This video is going to discuss the perfect square trinomial. And let's compare this to a difference of squares. So here was the difference of squares. I had something like x plus 6 times x minus 6. The binomials were almost identical, but they had the alternating signs. So one was addition, one was subtraction, and then this product ended up being two terms. A quadratic binomial, two terms. The difference is now I'm going to have the same binomial times itself. And the notation could look like this. This does not equal x squared plus 36. What this is telling me to do, this is telling me to take x plus 6 and multiply it times itself. X plus 6 times x plus 6. And when I do that, my first term is x squared. My second term is 6x, and then I have 6x again, and then I have 36. So when I combine like terms, I have x squared plus 12x plus 36. So if I make the assumption that this is true, I miss the linear term. So you can see that I miss the 12x, the linear term, if I leap to something like this right away. Let's do another one. Well, before I do that, let me just make sure that we see the comparison in the screen here. The difference of squares, the binomials are almost identical, but they have alternating signs, and the linear term sums out to 0. Whenever you're squaring a binomial, multiplying it times itself, that result is called the perfect square trinomial, and the difference is the sign in the middle stays the same for both binomials. Let's do a few more. Let's say that I have x minus 2 squared, and that's the way that the problem is presented. So what you're supposed to take away from that is to expand this properly, and that is the correct terminology. You're going to expand this. That means you're going to write it as x minus 2 times x minus 2. And this gives me x squared minus 2x plus 4. And then to clean that up, that's x squared minus 4x plus 4. And let's do one more, and then we want to look at it in the reverse. Let's do one with the lead coefficient that's not 1. So let's say I have 3x minus 5 squared. So this notation is telling me to expand this and then to multiply. So my first term, my quadratic term, is 9x squared, and then I'm going to have negative 15x and negative 15x again, and I'm going to end it with positive 25. When I combine like terms, and note that here I have a perfect square, and here I have a perfect square. So the perfect square trinomial begins and ends with perfect squares. And then the term in the middle, we'll look at that in class. Right now I just want you to get familiar with the terminology and the ability to expand properly and then to recognize a perfect square trinomial. Let's look at a few of the practice problems. Well, let's go back and look at a few of the practice problems before we go on to factoring. So here I have, and I believe this is page 103. Okay, so on page 103, you can see the way the problems are presented with the notation n plus 3 squared. So to expand this properly, this is what you need to do. And here I have y minus 7 squared. So to expand it properly, this is what you're expected to do. Number 5 is a difference of squares. Number 7 is the perfect square trinomial. So you can see the difference. Number 9 is also a perfect square trinomial. So in number 9, they've written it out for you. In number 7, you're supposed to know to do this. And then go ahead and multiply it out. I'll do number 1 with you, and then you can use some others by yourself. So this would multiply out as n squared plus 6n plus 9. And I will let you do the others. Note the difference here, plus and minus. It makes a difference for the sign in the linear term if the binomial is, if the operation inside the binomial is addition, or if the operation inside the binomial is subtraction. That makes a difference in the perfect square trinomial. In the difference of squares, the linear term would sum out to 0, so it doesn't really make a difference.